Hello, good afternoon, everyone. Let's go for another talk. This time will be Wojciech. Hello, Wojciech. How are you?
Hello, hello. I'm good. Thank you very much. Thanks for the invitation.
Can you tell your name properly? Because my
You all-
accent is terrible.
It's Wojciech. It's good. Wojciech. Yeah, it's a little bit softer than you do, but it was spot on.
Okay. So this is the sixth episode of Chatting Around the Campfire. Every other week we interview a fire safety engineering star. Today is Wojciech. Next week will be Tiago Oliveira, a Portuguese engineer that will talk a little bit about um, wildland urban interface fires. And 2 weeks from now, it will be Guillermo Rein from Imperial College. So, Wojciech, you are a fire safety engineer that sets stuff on fire for living as assistant professor at ITB Poland. I took this from your LinkedIn, I believe. So my question is, when did you start burning things? Still in your childhood?
It's deep in the roots. Like in a Polish culture, there is the children's tale of Wojciech who wanted to be a fireman. So I guess this really fits me. Um, as most of the people, I came into the industry by accident. In a way, I never planned to be a fire safety engineer, which is a pity that not everyone knows there's such a career path. But in a way, I was pushed onto these tracks of setting stuff on fire within the legal framework and not being chastened by police, which is quite nice. And yeah, I'm doing that professionally for at least 10 years. And I still have a lot of fun of doing that. And we actually really set things on fire, also buildings.
Which must be very fun, and you are paid for that, so which is great. So um, if just a tip for everyone that is attending us live on our Facebook page or in our YouTube channel, you can make questions in the comment line, and I will make those questions to Wojciech. So I also look to your Twitter profile, and you say you are a CFD artist as well.
Definitely.
Well, it's quite a resume. So the same. So is fire safety engineering an art?
Well, if you put that in this way, I think it is art. It's art and a science of engineering things that work based on the best principles and knowledge we have at a given time. And yeah, it is definitely a craft, and in many cases it is an art. The CFD artist is actually quite it is a pun and a joke from my side, obviously. As many people say, it's colorful fluid dynamics or cartoons for directors. So essentially, much of my work is focused on doing simulations, which end up in a bunch of pictures that can be shown to the investor. So he's very happy with the project, and he thinks and believes that the building as designed is safe or is not safe, and some changes must be made. So in the end, I end up using very sophisticated painting techniques, which are physically accurate. At least I hope they are. And so in a way, well, if you put it in this way, the CFDs is definitely an art, but it is also a craft and a difficult thing to do. And in one way, it's more approachable than ever to be a CFD engineer. Like it is so easy to start doing what you are doing as a CFD engineer. And on the other hand, it is so difficult to be good at it and to understand what's going on. You want to hear my first CFD attempt? I downloaded FBS and I've built a model of a wooden beam to burn it down. Like, what can be easier to burn down than a piece of solid wood? I mean, it's obvious. I was like in a third year of my university back then. My first beam did not ignite. The second one actually exploded. The third one burned like petrol. And 10 years later, burning wood and modeling pyrolysis is still one of the most difficult things I can think of, and I'm not sure if I could completely model that a priori before an experiment. So it is a magical world.
It's interesting that you mentioned that computer fluid dynamics produces colorful images. I love back of the envelope calculation methods and simple zone models, but nowadays it seems that those methods are not fancy enough for fire safety engineering community. And there's a lot of practitioners that use advanced software not knowing the basics behind the software, and that you can clearly understand when you are looking to a back of the envelope calculation formula. So did computer fire dynamics skill back of the envelope calculation models, methods like in the song Video Kill the Radio Stars?
And Spotify killed video. Well, that's a tough question and a difficult choice we make when we are doing analysis. In this world, it's sometimes more difficult to explain to your contractor why he does not need any CFD to prove a point, rather than just selling the CFD to him. Because you use the perfect word, fancy. It's a fancy method, it's advanced, and it gives realistic image of the phenomena you are investigating. I think it was Professor Statosopoulos from wind engineering who said that a really problematic moment is when your simulation gives you results that look believable but are false, because then it is very difficult to tell that the simulation is wrong. And because the entry point for CFD, for numerical analysis in fire, is so low, you don't even need to have a computer to start doing really high fidelity CFD analysis. You can rent computers at Amazon or any other place. Because the entry level is so easy, it's so simple to jump into this wagon. We as society kind of lose what built us in the 80s and the 90s, the simple models that were developed with the use of huge amount of experiments and huge collective experience of researchers. There was a golden era of fire research in the 80s and the 90s when we had so much great large-scale fire research that built beautiful models for compartment fire dynamics, but also models in other areas, like models for critical velocity in tunnels, models for plumes inside buildings, outside buildings. And a lot of these models are still highly relevant. And I really regret that in many projects, people do not take this opportunity to use a simpler model and prove a point. we actually with Piotr Fiło in SFP Warsaw, we had a whole talk about this, and it's still relevant. We are 5 years later, and it's still relevant. The simple models, their real potential, they can really shine now. If you take a look on what people are doing with the B-risk zone model, with the probabilistic methods involved in that model, it's completely new age for the zone model to be used, where you can perform thousands of simulations almost simultaneously and get your probability density function or cumulative density function as a result, and talk about outcome of multiple scenarios, not just one. It's very difficult to do that with CFD. In my office, I have a very, very powerful HPC computer we bought last year, and for us to run a 500 simulations is a matter of 2 months, and you can do that with the zone modeling within one evening on a laptop. So definitely there is huge power in the simpler models if you recognize their capabilities, recognize their limitations, and use them accordingly. And also in many cases, I think empirical models that are developed for certain use, for example, smoke plume models, you may actually achieve more realistic results with a simple model than with CFD, because if you're unexperienced with a CFD or on a budget with CFD, you sometimes make some cuts that really lower the quality of your results, but it still looks believable, and you are not sure that it's reality or not. For empirical models, you don't have to do these shortcuts, and you just use the model as it is. I would also like to comment that in Poland, CFD is very common. We have this building regulation that says that smoke control systems shall provide certain level of safety at evacuation routes, which is within the evacuation time, which is performance-based approach to define the criteria for a system. So in the end, we ended up simulating most of the smoke control systems in the country with CFD, because that's the probably easiest way to prove that the system is working. So they're very, very spread in Poland in terms of smoke control. How is it in Portugal? I think we discussed this some time ago.
Well, another thing, today I went to looking for a conference program, and I found this one. Okay, yeah. So almost 10 years ago, and back then I felt in this conference that there were clash between the ones that passionately defended real scale fires tests and those who truly believed, and I'm not joking, they believed that CFD models could represent reality better than real fires. So, in each side of the fence were you 10 years ago, in the CFD model army or in the real scale fire test side?
I think I was in the CFD army, actually. Yeah, I was more an artist than I am now. I would say now I'm more into the real scale fire test side. But also, as you said,
you moved to the dark side of the force then.
I'm taking power from both of the sides and combine them to become a Captain Planet. So yeah. But you said that some believe that CFD may represent a real fire better than a real fire. Well, actually, that's not completely untrue, because what a real fire is an outcome of the fuel, ignition, and the architecture. There's so many factors involved in the fire itself, and every fire will be different. If you set the same configuration of fuel into combustion in two different buildings, you end up with two different fires. And if if you go into parametric analysis with CFD and you really test your outcomes against a lot of different scenarios that happen, and especially if you use sophisticated methods to determine these scenarios, you actually obtain a range of valid answers on what the fire could be in the building. It's very difficult to do, and it's not something you would do as a CFD artist when you try to sell the analysis to your investor. But certainly there is a power in numerical methods that we may never have in the experimental side. The careful choice of boundary conditions and parametric studies, where you carefully alter one variable at a time to identify what is the impact of that one particular variable. That's something very difficult in full-scale fire tests, because the full-scale fire tests are they're very, very expensive. They're quite rare to be performed and very difficult to instrument. In experiments, you usually work with conditions that occur at the moment of ignition, in terms of wind, in terms of solar radiation, weather outside, the humidity of your air, the air temperature inside, pressure gradients. All of these things you must take as they are. Otherwise, you are doomed to wait for eternity for perfect conditions for experiment. And in CFD, however, it's easy to take each of these parameters as a variable, alter it carefully, and investigate the precise outcome of this alteration on the outcomes of your simulation. Obviously, only when you understand your simulation and only when you are sure that your simulation is a good representation of reality, if it's even possible. This is why experiments are still tremendously valuable for the community, because if we want to have CFD that's meaningful, and if we want to have simulations that are in a way a representation of reality and not just beautiful pictures of what might happen, then the experiments are the only way to fact check our CFD. And it is very difficult to simulate experiments, even if you have all the data you need, and if you have the ability to model experiment you have performed, it is still sometimes very, very difficult to pursue. And it's something that the University of Edinburgh shown in a classical Dalmanock study, when they've burned a bunch of compartments and made people do CFD analysis before and after in a group of Professor Rain and Professor Torero. It's a spectacular piece that's still relevant to what we're doing.
Yes, coming back to Eurofire 2011, and they did in this conference also that, well, the conference was hosted by Paris Fire Brigade, and they were very definitely in the real scale fire test site. And they organized a very interesting research trying to prove that performance-based design were doomed and CFD modeling weren't the way. So they hired 7 offices, fire safety engineering offices, to make 7 modelings of the same fire, and they provide accurate data in all fire loads, the same data for all the 7 offices, and it was a hotel, a guest room in a hotel, and they built 3 rooms exactly the same, and they burned the three of them, these 3 guest rooms. And from the 7 FDS simulation or CFD simulations, 5 had flashover, and 2 of them didn't, and 3 of the real test fires, two had a flashover and one of them didn't. So they had some problems trying to speculate or justify and elaborate on this, because the thing is, CFD models didn't reach the same result, but neither real fire test, real scale fire test. So my question is, how can performance-based design deal with chaos?
Yeah, that's a tough one, and you've reached a very difficult topic with that example of Paris fire, because it's not only CFD that failed them, but also the real fire that failed them.
Yes, that's the chaos.
And I've seen that in some of the experiments as well, where you wanted to reach a flashover, but someone did not, or the evolution of the fire was completely different than you would have expected. I've actually, in Poland, we are doing a lot of hot smoke tests. Hot smoke test is an artificial fire that we set in a building, not a huge in the size, it's probably a few hundred kilowatts, maybe a megawatt, with a lot of artificial smoke in it, and we do that to test the fire automation of the buildings. I have personally participated in probably 1,000 of these experiments, which resemble real fires in terms of spread of smoke fairly well. And so many times the outcome of the experiment was completely different from our expectations and our idea of what the spread will be, that I've learned a lot of respect to the chaos within the fire, that it really is something very difficult to predict. Even if you've seen the same fire 100 times, a simple change in your boundary condition in an inlet flow or in other aspect of the fluid mechanics of your compartment can completely change the outcome of the fire. So in the end, if you want to perform a single simulation and obtain a single complete answer to what a fire will be, you are doomed, and not because of the CFD being wrong. It's your question quite wrongly asked. If your question is, can this fire lead to a flashover, it's very difficult to answer this with perfect certainty, unless the conditions are, there are fires that will end in flashover, but sometimes they will, sometimes they won't. And the way how you ask the question is really meaningful for CFD calculations. This is why we do not really use CFD to investigate the growth of fire. This is why we don't use CFD every day to investigate complex effects like sprinkler and smoke interaction in our commercial work, because the uncertainties involved make this investigation more a guess. I mean, if you got the scenario correct, you may guess right. If the scenario is something else, you guess wrong. Only performing multi-parametric analysis or probabilistic analysis could lead you to an answer with a higher level of certainty that something may happen with a certain probability. But it's usually not the answer that people want. If you start talking about risk or probability, it's usually, they usually expect you to give yes or no answers. And can CFD deal with chaos, with PBD chaos? In Poland, as I said, we do PBD for smoke control. And for this, yes, the CFD is quite a good tool to investigate how the smoke is flowing through your building, through your area of interest, because that's what CFD does. It solves complex flows around complex geometries. And if you only are interested in how particularly the smoke entrainment will look, how the smoke will fill your compartments, move around your building, what will be the pressure gradients in your simulation, and so on, you obtain quite reasonable answers. Maybe not the perfect answer on how the outcome of the fire will be in your building, but if the question is my smoke control system able to control the consequences of this particular design fire, my CFD is a good tool to answer this question. And it may be a better tool than zone model or empirical model when complex geometry is involved. In these cases, you will not be able to answer this. So yeah, PPD can deal with chaos if we know what questions to be asked and if we use it for a certain, to find certain answers, which may not necessarily be yes/no answers.
Another one, will FDS continue to be the most commonly used CFD fire modeling software for years to come? I don't know if this is truly true in Poland. In Poland, you like to use other softwares besides FDS. So, what do you think?
I think, yeah, I think if you talk about the scale of use, the number of users, and the numbers of simulations performed with FDS, it definitely is and will be the most prominent fire-related CFD code. I personally work with ANSYS Fluent, and that's it's a different type of CFD model. It's more like a general code for CFD. It's a commercial code, and we use it because it is actually faster than FDS and has very good scalability on our cluster. So it's very efficient for us to use this model. FDS is one of the biggest achievements of fire safety engineering as whole. It was one of the biggest things that moved our profession forward, on par with the SFP handbook. These are the things that change the way how we look on fire safety engineering, and it's something that's given people ability to perform complex simulations in their home without access to very fancy models. So because of that, and it's still relevant today, 20 years after it was released, it still is the most approachable CFD code related to fire, with probably the best validation available, and still under development, still many passionate people are using it. But the problem with FDS is that you need to recognize what are the limitations of your CFD analysis, and you need to put particular attention to not cut the corners with this code. One example is, is mesh sensitivity. In 2007 or something, NUREC in USA performed some validation studies for FDS, where they determined a range of D-star number that relates your mesh size to the size of the fire. And with this magical number, you could say whether your mesh is appropriate for your solution or not in terms of entrainment. And this suddenly has become the ultimate mesh sensitivity tool people use around the world to have this D-star between 4 and 16. And if you look at it from a physics point of view, it is not necessarily the mesh resolution criterion you should be following. And maybe you should be using more detailed meshes than that come from that relation. And now the problem that there is every time you make your mesh twice smaller, you increase your computational time 16 times. And that is a huge issue for many people who use CFD commercially, FDS commercially, and many scientists who use FDS for their experiments. Because suddenly the time factor for your simulations, when they take months or weeks, is not acceptable for you. And you have to make a really difficult decision. Do I make my simulation coarser? Do I sacrifice possibly the quality of my study to obtain the results within a time frame that is satisfactory to me, or am I okay with having these month-long simulations? And this becomes, in a way, a limiting factor of the FDS. The solver is getting better and better every year. They improve everything, like every single aspect in FDS was improved if you compare version like 4 to 6.5. Every single aspect. But because of these improvements, the computational time increases, and it increases quicker than the computational capability you have does. So in the end, today, the same simulation takes longer than it took many years ago because of these improvements. And if your trade-off is to limit the capability of your software by choosing a wrong mesh size to have your calculations faster, you are burying the achievements of NIST and their collaborators who put all of their hearts to bring you the better solver. That's a problem I see with the way how community uses FBS, and I don't have a good answer to that. What can we do? They are doing a lot of optimization in terms of parallelization of simulations. Maybe one day we will be able to use GPU graphic cards for this, and that will be a huge jump in speed. I believe if that happens, that these will be absolutely the only rightful CFD code for Fire. But today, if you have to take time into account along with the models and the physics, sometimes the choices are very difficult.
Okay, I would like to recall people that is attending this chat online that they can make questions to Wojciech in the comment line, both in Facebook or in YouTube channel. Wojciech, we are talking a lot about CFD models, and when we look into conferences and articles about performance-based design, we see a lot of images from CFD and from software to estimate, to calculate egress conditions, evacuation, and modeling fire and evacuation seems to be the state of the art of performance-based design. But in ASET, FSET assessment, there's a lot other variables like human behavior and reaction time and detection time. So how can we model humans?
Yeah, that's ASET ERSET is a great. I'll take this question sideways. I will answer it, but I'll first start on a sideway. ASET ERSET is a great concept that precedes the ability to model smoke. It was developed in relation to sensors and primarily used with zone models. So that concept is older than our ability to use CFD modeling to resolve fire. And it's a concept that did not really change much since that time. We are still using it almost the same way as it was originally used, as a comparison if our tenability criteria exceed the threshold we set or not. And it is, in a way, something that failed to evolve in fire safety community, because there are probably ways that we can do this better than just using a threshold criterion to determine whether the conditions are safe or not safe in a space. And I regret that as a community we did not try to build on top of that. There are many aspects of acid calculations, such as visibility and smoke, which I'm passionately investigating to find answers in. Can we do better than just a number that says that in 475th second of your simulation, the condition became untenable? That's in my calculations, this is not the answer I'm looking for. Now, going back to people, can we model human behavior? Can we even tell how many humans there will be in a building? Let's start with that. Are we able to determine the boundary conditions of your simulations in terms of occupant distribution in your building? Can we define the most principal characteristics of your occupants, their moving speed, and even their size of your models, of your occupants in your model? These all are very difficult, and if you put human behavior on top of that and try to make a simulation of cognitive behavior of people, how they react to fire, to other evacuees, to other people, how they make decisions, this becomes extremely difficult task. But even though we may not have the answer how to model it perfectly yet, we are doomed to do that, and we need to do that because we need a reasonable way to estimate the parameters for our systems. We need to know for how long time our systems need to provide safety in your building so people can escape. So yeah, there are a lot of variables, and again, probably the simplest way is to go probabilistic with it and present your answer in terms of risk or probability functions. That, for example, with a confidence of 3 sigma, the people will escape my building in 5 minutes. That's a good answer. That's probably a reasonable answer that you can come up after a sophisticated modeling approach. Do we do that for commercial projects? No, not particularly. In commercial projects, we usually go with the most onerous scenario we can come up and just assume that this scenario marks the worst case, and if the people can escape my building in 5 minutes in the worst case, in most cases they should do that sooner. So my calculations are correct for that.
Yes, this was the question I have for you next, is how can we choose a fire scenario? Because normally we go for a probabilistic approach, but sometimes when we look to case studies of very severe and dramatic fires, they are not the most probable one. So aren't we playing God when we choose a fire scenario?
Yeah, but are we doing probabilistic analysis for that? I'm not so sure we are doing that in Poland, and I mean, it's also again a problem with the fire community. At some point in the golden era of fire research, we had people like Philip Thomas or Margaret Lowe or Howard Morgan, who were the authorities, and these smart people had to quantify some of the design scenarios so we are able to design with them. And an example, Howard Morgan and other members of CN committee on smoke control who are drafting European standards and British standards have proposed some sizes of fires like 4 megawatts, 8 megawatts, 6 megawatts, that then were repeated within the years as the valid choices of your design fire. So in the end, we stopped doing fire engineering of our buildings. We began standardized fire testing of our buildings with a CFD code. in a way, it resembles how standard time temperature relation for structural fire resistance was defined. It was based on a bunch of experiments performed in the late 19th and early 20th century. Then it was quantified into a certain time temperature relation that tells you how temperature evolves in the furnace. And then for the next 100 years, we use it almost unchanged, even though we recognize it does not anymore represent, or it did not never represent, a real fire. In a way, it became a standard test for your fire barrier. If your barrier passes this test, it means the barrier is good. Without questioning, is the assumption correct behind the curve? And the same happened to the common way we design our smoke control solutions and how we use CFD. We have these design scenarios that are quantified, that are written in standards, and we feel comfortable using them, designing our systems. And they don't necessarily answer the question, will the smoke from my fire safely leave the building I designed? But using this allows you to quantify that for this standardized hazard, my system works or not. So yeah, going to probabilistic design of choice of fire scenarios, that's more interesting approach. And I wish we could go full deterministic on that and we could just simulate the growth of fire in the building. But at this point of our advancement in fire modeling, we're not able to do that reliably. So going probabilistic is a way, but still you put new uncertainties into that because you have to define the probability density of your assumptions, which often are not known or difficult to obtain. So going probabilistic does not really take the responsibility of you that, okay, my design fire was probabilistic, so I was not playing God and the is above me. No, it's not like that. We're not playing God, we're playing engineer, and we're trying to use something that was developed in past and gave us reasonable results up to this date to test within the new designed solution will give more or less the same result or not. And now the big problem with that approach is that the world goes forward, the world goes ahead, and we suddenly end up with hazards that we do not have answers for. Take a look on design of car parks. They're very close to my heart, the car parks, because we've done a lot of them, and we like burning car parks. They're spectacular. And we have these nice design fires for car parks that were developed by TNO in Netherlands or CTCM in France or BRE in UK, or from full-scale fire tests under the hood, which quite well represent what a fire of a passenger vehicle is. And we know that how it grows, we know that it will have a peak that is rather sudden and rather large compared to the fire itself. We know that the duration of the fire will be something like 30 minutes and the total energy released will be something like 6 to 8 gigajoules. We know that. And we use that to design our car parks for many, many years. And next day, someone parks a Tesla in your car park or any other electric vehicle, and you suddenly have to ask the question, is my car park still safe? Because this hazard introduced to my car park is completely different than what I have used through the years and the hazards that my car park was validated against. And it's not only electric vehicles, it's also car stacking systems, where you put the car above the car because you run out of space and you need to put more cars in your car park. It's electric charging points in your car parks. This has it's hydrogen vehicles. It's natural gas vehicles. A lot of these things have never been considered when TNO was burning their cars in 1999. And today, that's still the best scenario we have to design our systems. And when you approve a design and say this smoke control system is safe, it provides the tenable conditions to the occupants, it does not lead to a catastrophic fire, you are, well, there are these challenges you have never tested because you didn't have a fire scenario for them. And that's a huge problem. And I'm even more worried about the hazards that we don't even know yet they exist. Because we design buildings. Buildings often live longer than their creators. And I have no idea what hazards we will bring into car parks in 20 years. But I would like my car park to be able to withstand them. That's a huge challenge, isn't it?
Yes, indeed. So we just to end this chat. Um, can you talk a bit about ETV and your fire research there?
Okay, yeah, great, thank you. Of course, I can talk about ITB. ITB is a Polish Building Research Institute, and we are the scientific institute that covers all the science related to built environment, not only fire, but all types of science related to built environment. Um, our fire research department is quite large. It's 40 people strong, and we have a very large and modern fire testing laboratory in Pionki in central Poland. For years, we were the workhouse of Polish built industry that was testing, certifying, and providing providing judgment over technical solutions related to fire. And in, let's say, last 20 years, it evolved also into some sort of consultancy that we are able to help people design better buildings in terms of fire safety. So we currently do a lot of standardized fire testing. We perform more than 1,000 standardized fire tests at ITB every year, which also includes approximately 200 fire resistance tests on furnaces, which is a huge number. And I'm not sure if any lab in Europe does this quantity of fire testing. We do a lot of CFD studies. We do a lot of evacuation modeling to provide our clients with answers on the questions that we help them ask. And we do plenty of that every year. This is why we are very well connected to the problems of real engineering. And the science we do, I often say it's selfish science, because we try to find out the scientific answers, or we try to use the scientific method to find the answer for questions for which we are not able to find an answer in the literature. So we're usually looking into white spots of research that we need for our own need, consultancy or testing, and we try to research them, and this gives birth to offspring topics and other interesting areas to research in fire science, but they all have a common root, which is real buildings and practical engineering. And it's something that I'm really proud of, that this is the way how we do research. My research topics, wind and fire, that's a huge thing for sure for me. I try to be as much wind engineer as fire engineer, and I really enjoy investigating what happens when wind meets fire. That's very interesting and problematic area. And in fact, most of the fires are in a way wind driven. So by not taking wind into account when we are talking about fire, we usually omit significant part of the fire itself. Second area would be visibility in smoke. that's something that for some reason I cannot really understand. I'm really passionate about, and I really like visibility and smoke modeling, reading all Japanese papers and building optical spectrometers, playing with lasers. That's really fun, and I also like it because it's one of the few research items I can do at my lab in Warsaw and without driving 100 kilometers to the Pionk lab. And we also recently do a lot of stuff related to the foundations of fire testing and relation between standardized fire testing and compartment fire dynamics to see to what extent fire testing is a representation of reality, and if it's not, how can we make it be a representation of reality? So yeah, that would be 3 topics. And facades, yeah. Facades are also big, and carports and many other things.
Okay.
And if you ever happen to be in Poland, I think you were in my lab, right?
No, you didn't invite me. No,
you're invited.
I arrived Warsaw in the day after the visit to your lab, so I wasn't able to.
I remember you chose morning jogging over a proper fire laboratory. But anyway, anyone watching, you're always invited to visit us. And if you find yourself in Poland, let me know, and I'll try to organize a visit. And trust me, it's always fun to see the lab and see how the fire science and testing looks in reality.
Okay, Wojciech, thank you so much for this time with us. And well, I hope to see you in the Berlin SFPE conference in March. But of course, we will be able to chat a lot meanwhile.
Well, let's hope it will happen. I hope that the particular circumstances that surround us every day are gone next year, and we can meet in a SFPE conference in Berlin. And I'm sure it's gonna be a fantastic event to take part. And I'm very grateful for inviting me to your campfire. Where's the campfire, by the way?
we were counting on you to make fire.
Okay, you should have told me. I would make a simulation of a campfire, and we could at least pop CFD in the background. It would make a nice background for the talk. Well, anyway, if you ever want to talk about how to break CFD, let me know. I'm here for you.
Okay, great. Wojciech, thank you so much, and see you next time. Thank you everyone that attended this conference, live or afterwards the record. Thank you. Bye.
Bye, guys.